Alright guys, we have a quick question here. This is from section 3.5, number 14. Now, here's what's going on here. We have two curves. We have this curve x cubed minus 3 times y minus 1, and the curve x times 3y minus 29 equals 3. These are both implicitly defined curves, and we want to know if these two curves are orthogonal. Now this is a new word, orthogonal. What orthogonal means, and this is the hint, or the definitions given in the instructions to the exercise. Orthogonal means that where these two curves intersect, if they intersect, at those points of intersection, the tangent lines have to be perpendicular. That's what orthogonal means. So you have two curves, they intersect, and they're both tangent lines at that point are perpendicular. Now, how do we have to judge whether two lines are perpendicular? We have to think about, going back to algebra class, the easiest way to check to see if two lines were perpendicular would be to take the product of their slopes, and if that was -1, then they're perpendicular. So let's say you have m1 and m2. If m1 times m2 equals -1, then those two lines with slope m1 and m2 are perpendicular. Okay, so if we're talking about the slope of this line and the slope of this curve and the slope of this curve, we need to find the derivative. Okay, now since these are implicitly defined, I'll probably find the implicit derivative. Okay, it might take a little work afterwards to clean it up. It might take some simplification, but I think I'll just go ahead and do that since they're already implicitly written. Now, I did notice I had a couple questions about this from a few students. I did notice one subtle thing in the homework exercise. The homework exercise asks us to find y prime here and y prime here. Now, typically we say that y prime is the exact same thing as dy dx, and it is in lots of instances. The one subtle difference is that dy dx it can be, the result dy dx can have x's and y's in it, and we're not really worried about it. But y prime means the derivative needs to have only x's in it. I'll talk more about that in just a few minutes. So that's why a few students were, a few of you guys were having some issues with this particular question, is because you guys were finding dy dx, which is completely fine in most cases, except that here we were asked to find y prime specifically, so both of our derivatives need to be in terms of x only. So we might have to do a little work to write those derivatives in terms of x only after we find dy dx. So let's see here. To find the implicit derivative here, we need to take the derivative of both sides of the equation with respect to x. So the derivative of x cubed equals the derivative. Now let's go ahead and I guess we can distribute here. We can say 3y minus 3. Okay, so what's the derivative with respect to x of x cubed? Well, that's easy. That's just the power rule. That's 3x squared. Okay, now what's the derivative of 3y minus 3? Well, the derivative of a negative 3 is just 0. The derivative of 3y is just 3. But since it was since we were taking the derivative of a y term with respect to x, we have to multiply the 3 by dy dx. Now, to solve for dy dx, we just divide both sides by 3, and we get that x squared equals dy dx. Now, since dy dx is written in terms of only x's, that is, it's only x squared over here, there's no y's over there, we can say that's equal to y prime. That dy dx in this case is exactly equal to y prime, because it's in terms of x only. So we're good there. That might not happen over here. We'll have to see. Now let's check this other one out. So there is our first derivative. Let's box that off. So x squared, we'll put a y prime over here. Y prime equals x squared. So there is our first derivative. I shouldn't say first derivative. There's the derivative of our first function. Now let's look at the other one over here. If we take the derivative of both sides of this equation, I'll just leave it as is. So we'll take the derivative of the entire right-hand side. That's x times 3y minus 29 equals the derivative of, with respect to x, of 3. Okay, now the right-hand side here, that's easy. That's just 0. It's the derivative of a constant. But this left-hand side over here, that's a quotient rule. Not a quotient rule, that's a product rule. We have the function x times the function 3y minus 29. So that's going to require a product rule. So we say that's the derivative of the first, which is just the derivative of x, times the second function, which is 3y minus 29, plus the derivative of the second function, which is 3y minus 29, times the first function, which is x, and then of course the right-hand side equals 0. So now the derivative of x with respect to x is just 1. So 1 times 3y minus 29 is simply 3y minus 29. But now the derivative here, okay, the derivative of 29 is just 0. That's a constant. But we take the derivative of 3y. We did that over here. We find that the derivative of 3y with respect to x is just 3 dy dx. But don't forget about that x over here. So times x equals 0. Now I need to solve this equation for dy dx. So I need to, let's see, subtract 3y from both sides, add 29 to both sides, and then divide both sides by 3x. So let's do the adding and subtracting first. So we could say that 3x dy dx equals, let's see, 29 minus 3y. And if we divide both sides by 3x, we can say that dy over dx equals 29 minus 3y over 3x. Now here's the one wrinkle, and I suspected this was going to happen. Okay, this dy dx, that certainly is the derivative of this function, barring me having made some arithmetic error. Okay, but the issue is this will not suffice for y prime, because y prime, we want to have only x's over here on the right hand side. Now there's an x and a y. So what I need to do is figure out what y equals and make the proper substitution. Now here we can do that because we could rearrange this and write it explicitly instead of implicitly. That is, let's see, what does y actually equal over here if I write it implicitly? Let's see, I could say if I divide both sides by 3, I could say that, I'll start here. I could say that 3y minus 29 equals 3 over x. Okay, I just divided both sides by x. I could then say that 3y equals 3 over x plus 29. And then divide both sides by 3, and I could say that y equals 3. Okay, let's combine this first before we divide. So that would be, let's see, 3 plus 29x over x, all divided by 3, like so. But then, of course, I could reduce this complex fraction and say that y equals, let me give myself a little more room. Y equals, okay, I'm going to have the fraction, let's see, 3 plus 29x over 3x. So we could actually define this explicitly in terms, the original function, we could write it explicitly. I don't know, that's a little more complicated, I think, but we can do it. Now we could say this is equal to y, so we can substitute this in here and get our function in terms of x only. So let's make that substitution and see what happens. This is going to take a little bit of algebra, but we could say that this equals, so I'm going to give myself a little room here, dy dx equals, okay, I'm going to have a really big fraction. There's still just going to be a 3x on the bottom. But on the top, I'm going to have 29 minus 3 times this entire thing. Because it's 3 times y, but this is y. So let's see, we have a fraction here. It's 3 plus 29x over 3x. Okay, now we have a little bit of simplification to do, so let's see here. Dy dx equals, so there's still just a 3x hanging out there on the bottom. Now we have 29 minus, what's the best way to do this here? Actually, oh, sorry, didn't mean to do that. Let us do this instead. Let's say that's going to be 29 minus 9. Actually, let's distribute this 3. So let's say, how do I want to do this? Oh, you know what? That's going to be, there's going to be a 3 there and a 3 there. We could just say that reduces to a 1 and a 1, but there's a negative sign out front, so we could just do this. We could say that reduces, let's see right here. So that right there and that right there cancel. So we're going to be left with plus a negative 3 minus 29x over x. Okay, so the 3's canceled out, but I distributed that negative sign. But the reason I did that is because I want to get a common denominator here. And let's say that's, instead of just 29, let's say that's 29x over x. So now I have a common denominator. So this is more algebra than I expected. Dy over dx equals, okay, we still have that 3x just hanging out there on the bottom, but now on the top we can say 29x minus 3 minus 29x all over x. Getting close here, I think. Now watch, we have 29x minus 29x, so that's, no x's. We're left with negative 3 over x all over 3x. Okay, almost there. Now this, if we think about how to divide fractions, we have a fraction divided by another number, so we flip this 3x and multiply. So that gives us negative 3 over 3x squared. Keep running out of room here. Sorry. So dy over dx finally equals negative 1 over x squared. So that is our y prime, our explicit derivative. Notice this is the exact same thing as, where were we? This right here. It's the exact same thing, but that's the implicit version. It has x's and y's. In general, if we can, we always want to write our derivatives with only x's, if possible. Here it was possible because we could solve this for y. It's not it's not trivial, but we could do it. And it takes a handful of steps of algebra, but we get that y prime dy dx equals negative 1 over x squared. Now let's write this up here and compare these two. So we have y prime equals dy over dx equals negative 1 over x squared. Now we're finally to the point, let's just say y prime just to be consistent here, y prime equals negative 1 over x squared. So now we are finally to the point where we can compare. Now we're finally to the point where we can talk about this orthogonal business. Remember, orthogonal means that where these two curves, this curve right here and this curve right there, where they intersect, and then you'd have two tangent lines, one for the first curve, other for the second curve, those two tangent lines have to be perpendicular. And to be perpendicular, this property right here has to hold true. Okay, so let's see. If you take, let's say this right here is M1 and this right here is M2. First slope and second slope. If you look at M1 times M2, well, that's x squared times negative 1 over x squared. What do we get? Negative 1. And that's exactly what we needed to happen for these two slopes, these two tangent line slopes to be perpendicular. So we have just shown that these two curves are orthogonal. If we had multiplied these two derivatives, these two slopes together and gotten any number besides negative 1, then the result would be not orthogonal. Okay, not orthogonal. But since we get a negative 1 here, these are orthogonal. Okay, so these two curves are orthogonal. Now, there would be, I think, let's try it out. There might be an easier way than using implicit differentiation. Like, we could have, is it worth our time? Let's see. If we first define this curve explicitly, we just did it. It's right here. This is the explicit definition of this curve. And if we do the same thing here, write the explicit definition of this curve, we might have arrived at our solution a little bit faster. I don't know how much faster. We can see real fast. For instance, how would we rewrite this function, this equation explicitly? Well, we solve for y. Let's see here. If we solve for y, we will get, okay, if we distribute our y minus 1 here, so we would have x cubed, just a little bit of work off here to the side, we would have x cubed equals 3y minus 3. So we would add 3 to both sides and get x cubed plus 3 equals 3y. Then we would get x cubed plus 3 divided by 3 equals y. So it turns out it was actually pretty easy to write our two functions in explicit form. So here is that function, and here's that function. So we could differentiate both of these, and we should get that answer for this derivative and this answer for this derivative. Let's double check to make sure we do get those answers. It might turn out this way is a lot easier than doing these implicit derivatives. Let's see. If we take this derivative here, that is, find y prime, we could say that y prime, now you could use, a lot of people are going to resort to the quotient rule here. You don't have to use the quotient rule. We could factor out that 3 on the bottom. We could say this is 1/3 times the derivative of x cubed plus 3. So that gives us 1/3. Now what's the derivative of x cubed? Well, that's just 3x squared. What's the derivative of 3? Well, that's just 0. So we get 1/3 times 3x squared, which gives us x squared that exactly. So that was easy, but that derivative right there was easy to start with. Both, so the implicit and the explicit derivative were very easy in that case. Let's try this one. Now that does require a quotient rule there, because we have a variable in the bottom and a variable on the top. So let's take that and see what happens. Okay, so let's do this derivative. Let's do it, and let's do pink, I guess. That's fine. So we could say, let's go over here, and let's say y prime equals, actually, let's give ourselves a little more room. Y prime equals, okay, we have a big fraction here. Now it's the derivative of the top. So the derivative of the top, again, we're just dealing with x's here, so it's 3 plus 20 on an x times the bottom, which is 3x, minus the derivative of the bottom, which is 3x, times the top, which is 3 plus 29x. Sorry, I almost ran out of room there. Okay, all over the bottom squared, which is 3x, everything squared. So let's see what we get here. It's still going to be a really big fraction to start with. Now on the bottom, that's going to be a 9x squared, so we can just go ahead and do that. Now let's see. The derivative of 3 is 0. The derivative of 29x is just 29. So 29 times 3x is what we get there. Minus, what's the derivative of 3x? Well, that's just 3 times 3 plus 29x. Now this is going to take a little bit of simplification here. Let's see. We have, still that 9x squared on the bottom. 29 times 3x, that is 87x. Let's see. Negative 3 distributing here, that's negative 3 times positive 3, so that's negative 9. Negative 3 times 29x, so that's negative 87x. Yep, here we are. So we have 87x minus 87x. Then we have negative 9 over 9x squared, which gives us negative 1 over x squared. Oh, sorry about that. Meant to do this. Negative 1 over x squared. That is the exact same answer we got there. Now, was that easier? I don't know. I mean, I think it actually was easier in that case because the implicit derivative here is all in purple. And so it took a lot of steps not to find the implicit derivative. The implicit derivative was just this here. But it took a little bit of, not a little bit, it took 3 or 4 steps of algebra here, maybe 4 or 5 steps rather, to get the explicit definition. So there we do get the same thing. So I think first converting this to explicit form and then taking the derivative ended up being easier. You get the same answer either way. The only thing you have to be careful of is that if you do what I did there in purple and find the implicit derivative first, that you have to make sure that since we're asked to find y prime specifically, that we go ahead and write the derivative in terms of x only, since we can in fact do that. We can easily solve this for y, which will allow us to write the derivative y prime in terms of x only. So again, just to conclude, just to recap here, that these functions are indeed orthogonal because at the points where they intersect, the tangent lines are perpendicular. Now I actually graphed this, so I'll show you real fast. Here are these two curves. Okay, so here are the two curves. The blue curve is x times 3y minus 29 equals 3, and the red curve here, which it's kind of like a cubic, or it is a cubic, is that's the x cubed equals 3 times y minus 1. Now see here, they actually intersect at 2 points. Now they intersect here at a not very nice point. You know, it's actually an irrational answer, I believe, there. But here they intersect at a pretty nice point. So I went ahead and graphed the two tangent lines. So if we zoom in a little bit here, so these two curves intersect at the point 310, which is kind of nice. Now the red curve, if you see here, has this green tangent line, and the blue curve has this orange tangent line. And I think you can see that the orange line here, the orange tangent line, and the green tangent line are indeed perpendicular. So that means that, that's what it means to be orthogonal. That at this point right here, where these two curves intersect, you have the red curve, and I know it's kind of close here, but you have a red curve right here that's intersecting a blue curve at the point 310. We have both tangent lines drawn, the tangent line to the blue curve and the tangent line to the red curve, which is which results in the orange tangent line and the green tangent line, and those two tangent lines are perpendicular at this point. So that's what it means to be orthogonal. And if we did the same thing down here at this point of intersection, we would find the exact same thing. Now the reason I didn't do this here is because the solutions are irrational, so more decimals, more arithmetic to work with there, so I didn't really worry about it. But here the solution was nice, so I went ahead and graph these tangent lines. Okay, so that's what it means to be orthogonal. I hope this helps. If you have any more questions, just let me know. See you soon.